Welcome back. So in the previous session, we read our references using BIP2DF data frame. And then we have read about 600 observations in the COVID and 826 observations for SARS. And if we look at one of our, they have 32 variables each, so it's all the variables are exactly similar, and these are the variable names, and we have category, BIP text key, address, anode, and then it continues until the last part, which is about PMID. So that's the PubMed ID at the end, and the language and all the records they are extracted, they are directly converted using the BIP2DF reference, the BIP2DF package actually. But since we have 32 variables, I don't need all of these variables. I only need some of the variables, so I just need to select. So I'm using the dplyr package to select only, to filter my data. Actually, first I need to make sure because I'm doing text analysis on abstract, like the abstract of these records. As abstract is in in scientific literature, is a summary of your summary of your paper actually, so a summary of your article. So I will only need abstracts that don't have any missing value. I need all records that don't have any missing value in abstract. So I need to filter all of these records with no missing value, because I need the complete data for this. So then after that, I need to select only a handful of the variables that I need. For example, because I'm doing text analysis, I need a text data, and that is probably, it could be abstract or title or keyword maybe. But I'm for this text analysis, I'm mainly interested in abstract. So I will only take abstract and other reference, other few variable names. I don't need much of these 32 observations. I will only select the year, title, abstract, keyword, author, and BIP text key. That's all. I don't need any other. So let me read this again. So I will move all the other variables. Let me read this, and then for the next one, I will also need the same. So I will simply copy this until otherwise the rest of the syntax will be the same. So I have 6 variables, 442 observations. So that means there were about 100 something. You remember this was 600, now it's 442. So that means there were about 158 references that didn't have abstract. So there was missing value in abstract. So we are now complete. Our abstract is complete data. So in the next one, we are also removing missing values, data observations that have missing value in abstract, because that's the data that we are going to do text analysis, and we don't want any missing value. So we need a complete data for that. Then after that, we will select only these variables, the same as the previous one. So if you remember, we have 826 observations and 32 variables. In the next one, this will change to somehow 600, or I don't know, let's see. Yeah, so 433. So luckily they are nearly the same. So we will not worry about balancing, because we are doing machine learning later on. So machine learning, you would hope to have your data to be balanced. Balanced if you have dichotomized outcome. So let's say if you have disease present and absent, you wish to have like 50% of the outcome on one side and 50% on the other side, so that your machine learning model perform better. Otherwise, your machine learning algorithm will be dominated by one outcome, and the prediction will be maybe on one side. So there may be bias. So you can avoid this bias by balancing. There are balancing strategies such as up sampling, down sampling, So you can, or also synthetic minority oversampling technique, something called the SMOT. You can do that, but for this purpose we are not going to do anything like that because we have a balanced data set, so we don't worry about it. The next thing we want to do is assign. So let's say we need to assign, because the first one is about COVID, second one is about SARS. So we need to make sure type, the type of, let's say if you want to you are working on a systematic review or something, and you are taking all COVID papers and you are excluding, let's say you are doing some like some publication analysis or something. So you would include all articles published for COVID, and you will exclude all papers for SARS. So that's so we create one variable, and if the articles are from our previous data frames, is because this is all about COVID, and we assign it as 1. So that 1 is the outcome that we have. And SARS, because SARS is, we don't need it, we are excluding it, so let me assign it as 0. So that means I will have another variable. Then once I have identified this, what I need is I need to combine the two data frames. So that means I need to merge them. To merge, I don't need any other package or something. I just simply use this rbind, and then COVID and SARS will be, the two tables will be one on top, and the next one will just be appended on the next rows. So all this 442 and 442 and 433 references, they will be appended. I have some minor issues with my PC. Yeah, let me run it. So once I run that, so it will be merging the two. So now I have 875 observations and 7 variables, of course, because we just added 1 variable. The next thing I need to do is let me just have a quick look of my data. Maybe I can use a glimpse function from dplyr. Oh God, this cursor is lost. I don't know. Let me just pause the video and maybe come back later. Yes, so what we do is we combine COVID and SARS recorders, and we will see the two data frames are combined. So that means we have 2 of them. But the good thing, we identified them. To identify them, we already created this include, a new variable, and we have assigned for COVID articles, we have labeled them as 1. So that means they are positive outcomes. And then for the other ones, we have already said 0. So that means it's not COVID. So the other thing we can do is we can check, if you want, what we can do is table, we can create table, and to create to see how they are COVID SARS, and then we do include, then let's see how. So you see 433 SARS and 442 COVID. Then if you want, we can also see the proportion prop table. Then yeah, so it's 49%, 49.5% are SARS, and 50.5% of the papers are COVID. So that means it's almost 50-50. So we don't worry about balancing or anything, or doing anything like that. The other thing I would like to do is I want to assign. So this instead of 0 and 1, let me add some value labels. So to add value labels, what we do is we can add this COVID SARS. Then once you have COVID SARS, you take the dependent variable. That's the variable that we want to do, include, and then you put it in a square bracket, and then So if it is 1, that means if it is 1, we will assign it as COVID. Let me just use this COVID. Then for the next one, let me just copy this and put it down here. Then I will assign this into 0. So if it is 0, then it will be SARS. This is just the bizarre way of labeling a variable. Otherwise, you can also do it using the dplyr or whatever way of labeling the data you have. So let me just run this. Then I will, yeah. Now if I do that, so it's COVID, 50% of the data is COVID, and 49% are about SARS. So that means you see, yeah. So that's how it is like that. The next thing we need to do is we need to, as I said in the previous in the PowerPoint, we have said we need to split the data. So we need to split our data into train and test set. To split the data, we need you can do it using sample or another package, but I will just use Caret. Caret package is a very popular package actually for doing tuning machine learning models. So I will just use the Caret package to split the data. And then splitting the data is about sampling. So you take sampling. So if you do sampling, then you have to make it reproducible. Otherwise, every time you select a sample, then it will not be the same. So the same number of the same type of the same number of observations will be selected, of course, but the observations that will be selected in one sample may be different from the observations that are selected in another one. So you need to make it reproducible. Make sure that you don't, if you are really doing real scientific analysis or something that you will report in your paper or something, then you need to use this. Otherwise, people cannot reproduce your code. This is for reproducibility. So your sampling can be reproducible. Then Caret index tells us to first to create the train index. So we can create train index, and then we use create data partition. This is the function that we use. So that what you use is like create data partition, and then the y variable, of course, the one we say include. Then how many times it should be. The next is times, and that means how many times that observations can be selected. You say there is, when you sample, there is sampling with replacement and sampling without replacement. So in this case it's sampling without replacement. So that means an observation can be sampled, but so it will not be sampled again. But if you use sampling with replacement, then you take that observations and then put it in your sample, and then you bring it back and put it and the original. So then you may probably sample it again. So that means there will be a chance to sample it over and over again. So that means you change this number if you do sampling with replacement. So in this case, we are not doing sampling with replacement. We are instead doing sampling without replacement. Then you take the p, and that depends how you want to assign for training set. Are you doing 70-30 or 80-20 or 90-10? So in this case, in our case, we are using 70% for the training set, so we will use 0.7 here. And let me just use this create data partition. And the first thing that we use is we use our dependent variable, which is include, the one we say, and then we create the p, and that is we say 0.7 because we are using 70% of the data set for the training set and 30% of the data set for the test set. Then we say times equals 1 because we are not doing any sampling with replacement, so we are using sampling without replacement. Then once you do this train index, what train index does is it assigns an index value. So for all observations across this COVID SARS, so it gives them an index, at least index for observations that are selected to be on the training set. So 70% of the observations will have a train index, and then that means we need to have another code so for making that. So then what we do is train, and then you take your data, that's your original data, and then we add the train index. And that's we put it at the first instead of, because if you have data, and then let's say if you write something 2, 3, so that means so your data, second observations, third column. That means second observation and third column. But if you do this data and all observations, but only the third column. But if you do this 2, and that means you only want the second row. So in this case, we are looking all the index values that are for the label for the observations. So that means you need train index just before the comma. So that means you will take all the index values, all observations that train index value is assigned for. So that means train, and if we run this, we have the training data. So we have 614 observations. This is just an ignorable error because this is this is just because the package wanted to be a table or a matrix. Can't matrix of us. Yeah, it's because it's just the table package. So you can ignore it. Second thing that I want to do is I want to identify my test set. So I can copy from the previous code and the test set. And the next thing, this is a complement of the other because it's the opposite, because we have already said 0.7. So in this case, we want to identify all the observations that don't have any train index value. So then you add minus sign. So once that, you can have your test set. So we have already our test set. Then from this point on, we can do our text analysis because we have our data ready for text analysis. And the next thing is we do our text analysis. And to do our text analysis, as I said, we need Quanteda. We are not doing tidy text. We are not using tidy text in this case. And we simply continue with our Quanteda text analysis in our next session. So thank you for following up, and I recommend I would like to ask you to share or subscribe, or maybe give it to someone who is interested in doing biomedical text analysis. So this is actually something that may be really applicable in systematic review. So if you are doing systematic review and meta-analysis, or if you are if you search literature and you do lots of screening, title abstract screening, then you have to do, if you have lots of papers, then you have to do a lot of manual work. But if you apply machine learning, you can really reduce the screening workload. I have worked a lot on it, and I have reduced my screening workload by 65%, 63%, 60. So yes, it really really helps a lot to reduce screening workload. So there might be people who are interested, and I'm sure there are people working on it.